Welcome to another edition of The Explainer. I am absolutely thrilled you're here today because, well, we're tackling a topic that perfectly bridges the gap between high-minded idealism and cold, hard reality. We are looking at the hidden math behind renewable energy. Okay, let's dive into this because replacing conventional fossil fuels with renewable tech is obviously great for the planet, but it introduces an entirely new set of financial hurdles that we really need to understand. Does going green actually save you green? I mean, this is the million-dollar question, right? Literally. There is this massive tension between the incredible environmental benefits of ditching fossil fuels and the very practical reality of whether these renewable projects actually make financial sense for a business or a homeowner. Because look, at the end of the day, a project might drastically slash greenhouse gas emissions, but if it bankrupts the company trying to implement it, yeah, it's never going to get built. To resolve that tension, we rely on something called engineering economics. Think of it as the technical and economic mathematical framework that investors, engineers, and business owners use to decide if a renewable energy project actually gets a green light. It's basically the ultimate tool for comparing competing technologies and figuring out the true total cost of a system over its entire lifespan. We're not just looking at the price tag you see on day one. Let's move to our roadmap for today and see how this builds. First, we'll cover the economics of renewable energy. Second, the time value of money. Third, life cycle cost analysis. And fourth, understanding payback periods. So, starting off with Section 1, Economics of Renewable Energy, the cost breakdown. Every single engineering project essentially involves a high-stakes tug-of-war between two very different types of money. On one side, you've got your capital costs. This is your initial investment, buying the solar panels, paying for the installation labor, all those startup expenses. Boom, it hits you all at once at time zero. On the flip side, you have operating and maintenance costs, or O&M. These are the ongoing expenses just to keep the system running over its lifetime, like routine cleaning or, crucially, the cost of the electricity or fuel it actually uses. The fundamental challenge with renewable energy is that it almost always demands massive upfront capital costs, but promises incredibly low operating costs down the line. Fossil fuel systems are often the exact opposite. So how do we fairly compare them? That brings us to Section 2, the time value of money, why timing is everything. To make a genuinely fair comparison, we really have to understand the most important rule of finance. Imagine this scenario for a second. Someone offers you $1,000. Would you rather have it right now, today, or exactly 1 year from now? You want it today, of course. But why? Mathematically speaking, it's because money is always in shortage, and its value literally changes with time due to interest, inflation, and taxation. If you simply add up incomes and subtract expenditures over a 20-year project without adjusting for time, well, your math is going to be completely wrong. Let me show you exactly why. If you take that $1,000 today and put it in a bank paying a 6% annual interest rate, in 4 years it turns into $1,262, and this brilliantly illustrates how compounding exponentially grows money over time. Because of this compounding effect, an expense of $1,000 10 years from now hurts a whole lot less than an expense of $1,000 today. But, the real world is messy, and the taxman always takes a cut. We can't just use simple interest. We have to use inflation and taxation-adjusted interest. Inflation eats away at the buying power of your money, and taxes take a big bite right out of your interest earnings. For example, say you have a great 8% interest rate, but inflation is running at 3% and there's a 2% tax on your interest. Well, your actual adjusted interest rate plummets to 4.7%. When evaluating a 20-year wind turbine project, using that 4.7% reality instead of the 8% fantasy makes an absolutely colossal difference to the bottom line. Moving right along to Section 3, Life Cycle Cost Analysis, the big picture. Now that we know money changes value depending on exactly when it's spent or saved, this is where we apply these time value concepts to the real world. A life cycle cost analysis, or LCC, is how we compare competing project options. We calculate their total costs over their entire lifetime, but we don't just lazily add up the numbers. We use the net present value, or NPV method. This clever formula takes all those future operating costs, future maintenance bills, and future energy savings and mathematically translates them back into a single present time dollar amount. It totally levels the playing field. Let's look at a fascinating case study straight from our source material. I like to call this the motor showdown. Imagine a facility needs to buy an electric motor for a renewable energy application. Here are our constants. The motor needs to output 45 kilowatts. It's going to last 10 years. It runs 4,000 hours a year. Electricity costs 10 cents a kilowatt hour. Maintenance is fixed at $500 a year. And our interest rate sits at 8%. The facility has 3 options to choose from: standard, high efficiency, and premium. Now, what's really interesting about this comparison is the initial cost. If you're a procurement manager working with a tight budget, that standard motor looks absolutely amazing at $11,000. The premium motor is 94% efficient, which is undeniably great, but it costs $14,500. That's a massive $3,500 markup on day one. Honestly, if you don't know engineering economics, you buy the standard motor every single time. But look what happens when we calculate the net present value. When we actually factor in 10 years of electricity consumption and discount all those future electricity bills back to today's dollars using our 8% interest rate, a massive twist occurs. The premium motor is actually the cheapest option. Over its entire life, it costs a total of $101,400 compared to $103,600 for the standard motor. The highest initial cost wins the long game, saving the company about $2,200 overall. Finally, Section 4, Understanding Payback Periods. When do I get my money back? Even if a project has a fantastic net present value over 20 years, every business owner is going to ask one simple question before they actually sign the check: when do I get my money back? This is the payback period. It is simply the amount of time it takes for an investment to entirely pay for itself through the annual savings it generates. And here is the harsh reality of the business world. The payback period absolutely must be shorter than the life of the project. But more importantly, in today's economic environment, it's really difficult to get boardroom support for a project if the payback period stretches any longer than 3 to 4 years. So the crucial point is making sure we calculate this correctly. Most people use a simple payback period. You just divide the initial investment by the annual savings. It's super easy, but it's mathematically flawed because it totally ignores the time value of money we just talked about. Engineers, on the other hand, use a discounted payback period. This uses complex logarithms to account for the interest rate. It represents mathematical reality. And here is the warning you just cannot ignore. The simple calculation always underestimates the true time it takes to break even. Look at this incredible example comparing a solar PV system to a trombe wall, which, by the way, is a type of passive solar building design. For the solar PV system, the simple payback looks pretty okay at 6.36 years. But when you factor in a 6% interest rate, the discounted payback leaps to 8.25 years. It takes almost 2 full years longer to pay off than the simple math suggests. Meanwhile, the much cheaper trombe wall has a discounted payback of just 3.13 years, easily sneaking under that critical 4-year boardroom threshold. But I want to leave you with this vital, grounding thought directly from our source material. Sometimes, some benefits of a project are difficult to be expressed in monetary terms, and their existence can be a deciding factor for a green light. As much as we've focused on spreadsheets, formulas, and interest rates today, reducing greenhouse gases, eliminating pollution, and, protecting humanity, well, they often defy a strict dollars and cents calculation. Engineering economics is the foundation. It tells you exactly what a project costs and exactly when you'll break even. But it's up to you to weigh those numbers against the future of our planet. So I leave you with this. What unquantifiable environmental benefits will justify your next green light? Thank you so much for joining me to explore the fascinating economics of renewable energy. Keep learning, keep analyzing, and I'll catch you in the next explainer.